Hello, everyone, and welcome to today's presentation. I'm excited to introduce our topic. What are photovoltaic cells? Photovoltaic cells are the core component of solar panels, and they play a crucial role in converting sunlight into electricity. Today, we'll explore how this process works, starting with the basics of the photovoltaic effect. We'll look at how sunlight excites electrons within the cells and how that leads to the generation of electricity. So, let's get started and uncover the fascinating science behind solar energy. Let's talk about the materials used in photovoltaic cells. Most PV cells are made from silicon because of its unique semiconducting properties. Essentially, silicon can conduct electricity, but only under certain conditions, which makes it ideal for solar energy conversion. To make silicon more effective, it's treated or doped with other elements, like phosphorus and boron. This doping process helps create two different layers within the silicon, a positive or P-type layer and a negative or N-type layer. The N-type silicon is doped with phosphorus, which introduces extra electrons, giving it a negative charge. On the other hand, the P-type silicon is doped with boron, which creates a lack of electrons. These are called holes, and they act like positive charges. When these two layers are brought together, they form what we call a p-n junction. This junction is absolutely critical because it generates an electric field. This electric field is what drives the movement of electrons when sunlight hits the cell, ultimately enabling the conversion of sunlight into electricity. So, the choice of silicon and how we manipulate it directly impacts the efficiency of the PV cell, tying into the overall theme of harnessing solar energy effectively. Let's walk through how sunlight actually turns into electricity, starting with the first step. When sunlight hits the photovoltaic cell, the energy from the photons is absorbed by the semiconductor material. This is a crucial moment because it kickstarts the entire process. Next, that absorbed energy excites the electrons within the material. Think of it like giving them a little boost. This excitement causes them to break free from their atoms and start moving around freely inside the cell. Now, when these electrons are freed, they leave behind what we call holes. These holes are essentially positive charges that act like the absence of an electron. They play a key role in creating the electric field needed for current flow. Moving on, the electric field at the p-n junction then pushes these free electrons toward the n-type layer, while the holes naturally move toward the p-type layer. This movement of charges is what creates an electric current. It's the fundamental process that converts light energy into electrical energy. Finally, the flow of this current is captured by metal contacts on the surface of the cell. From there, it's directed through an external circuit, providing usable electricity for your home or device. And that's how sunlight, through a series of exciting steps, becomes the electrical power we rely on every day. Now let's talk about how the electricity generated by PV cells works. The electricity produced is direct current, or DC, which means it flows in one single direction. But here's the thing, most household appliances are designed to run on alternating current, or AC, where the current changes direction periodically. So to make that DC useful at home, we need a device called an inverter. The inverter converts the DC into AC electricity, allowing your home or business to be powered efficiently. Next, you might wonder, why is silicon the material of choice for PV cells? Well, silicon is incredibly common. It's abundant in nature. It's also non-toxic, which is great from an environmental standpoint, and importantly, it's very efficient at turning sunlight into electricity. That said, researchers are always working on new materials like perovskite to push efficiency even further and reduce costs, making solar energy more accessible for everyone. Finally, let's look at some real-world applications. For example, residential solar panels are installed on rooftops to power your home appliances, charge batteries, or even send excess energy back to the grid. Larger solar farms are built on a massive scale to supply power to entire communities or regions. And for outdoor enthusiasts or those in remote areas, portable solar panels are a handy solution for charging devices or providing power where grid access isn't available. These examples show just how versatile solar technology has become in our daily lives. This slide doesn't contain enough information. That's why we're moving to the next slide.